Hi everybody, this is Jim Corkins. We're going to be covering 1D free body diagrams with multiple objects interacting with each other. So please read Coletta chapter 4 and 5. This is related, if you're taking Physics 111, this is related to homework 7 and 8. Homework 7 is 1D forces, homework 8 is 2D forces. If you're in Physics 121, you're going to do Sapling homework 4, which is 1D forces, and homework 5, 2D forces. In the 111 and 121 lab books, this will be labs 5, 6, and 7. Problem-solving strategies for interacting objects. You're going to identify the objects that are interacting with each other. So then what you're going to do is you're going to draw the non-contact force mg for each object and then the contact forces on each object. This will be done in a free body diagram. The one important caveat to this is if the two objects are touching each other, there is going to be a force of one on the other. Usually if it's objects AB, I'm going to have it force with capital F sub AB, and one will be positive, and on the other object, since forces are equal and opposite, Newton's third law, you're going to have to draw a negative force sub AB for the other object. If there's a rope attaching the two objects, you're going to have to draw a tension force on one object, and then negative tension force on the other object, and they'll be labeled the same tension force. So if they're both T1, for example, it would be T sub 1 on one object and a negative T sub 1 on the other objects. The objects ropes are always pulling, and they will be, again, Newton's third law, they will be pulling opposite each other. Then what you'll have to do is you're going to have to apply Newton's second law. And that would mean you're going to have to sum the forces in the x direction and sum the forces in the y direction on one object and do the same for the other. At that point, you're going to have to solve for whatever they're asking for. When you're solving just make sure you pay attention to the units as always. And when you complete it, make sure that your answer makes sense. So here we have a practice problem. We have box A, which is 4 times the mass of box B. Both are being pulled to the right by a string, T2, with a force of 8 newtons, and it's speeding up along a frictionless surface while moving to the right. So what we were supposed to do in here, we were asked to find the acceleration for both objects and also compare the tension in rope 1 to the tension in rope 2. So pause the video in a second. What I want you to do is I want you to ask yourself how many forces are acting on box A and how many forces are acting on box B. So go ahead and pause the video right now. So you've thought about the number of forces acting on block A or interacting with block A, and also the number of forces interacting with block B. So let's go ahead and begin drawing a force diagram. So I'm going to give a little mark for block A. And give another mark for block B. This would be our little black dot if we were drawing since we're drawing free body diagrams and we have two objects, I want to distinguish between them by an A and a B instead of a black dot. So it looks like object A has 3 forces working on it. It's got the non-contact force due to the weight of the object working by the earth. It's got 2 contact forces working on it, a string or a rope, and also the surface. So I'm going to pause right now and begin drawing that force diagram. Okay, I'm going to begin drawing the non-contact force due to the weight of the object. And that is mass sub A times gravity. There's the surface working on this, which is also called the normal force. And I'm also giving that a normal force sub A, and that is pointed up. This one is pointed down. All right. I drew those to be about the same size because the object is not accelerating in the vertical direction, it's only accelerating in the horizontal direction. So the normal force in this case should be equal to the weight of the object. All right. There is a rope or a string attached to this, and it's being pulled to the right, and it's got a tension T1 in the string, and since it's pulled to the right, it's got a positive tension for the direction of the force. Okay, how many forces are working on block B? You should have said 4 forces. Block B also has a mass, so therefore it's going to have a weight, mass B times gravity. It's got a rope working on it, T1 to the right, on the right, attached to the right of the object. It's got another rope, I'm sorry, that was T2. T1 is attached to the left of the object, and then it's also got a surface acting on it. So go ahead and pause the video and draw a force diagram for that. Okay, so let's go begin by drawing the weight of the object. Now, since this box has 1/4 the weight of mass A, I'm going to draw mass B times gravity to be much smaller. And I'm not sure what the proportion, the proportion should be 1/4, so I'm going to try to get this arrow to be kind of close to that, but at this point we're just trying to distinguish it to be smaller. Right? It's also going to have a normal force up. That normal force is block B, pointed up, it's got a vector head on it, and again, since there's no acceleration in the vertical direction, that these two arrows should be the same size. A rope is attached to the right hand side, pulling it to the right, and that is T2. Sorry about that. And T1 is attached to the left hand side, pulling it to the left, and it's negative because the arrow is pointing to the left. All right, how was your force diagram? All right, what I want you to do now is I want you to translate these two force diagrams into using Newton's second law. So create equations from them. Okay, so what I'm going to do is sum of forces on object A in the x direction, and then I want you to sum the forces on object A in the y direction. And I want you to do the same for object B. Object B, you're going to sum the forces in the x direction on object B, and you're going to sum the forces in the x direction on object B in the y direction. Go ahead and pause the video right now and sum those forces for me. All right. Object A, in the x direction, it has only one force, which is T1, pointed to the right, so it's positive. And that is going to be equal to mass A times the acceleration in the x direction. And supposedly these are acceleration vectors. In the y direction, mass A has a normal force up. It's got a mass times gravity down. And I'm going to go ahead and move these guys over here. So give myself a little bit of room. And I'm going to set this equal to mass times acceleration in the y direction, but in this case, there is no acceleration in the y direction, so that acceleration vector is 0. For mass b in the x direction, I have t2 pointed to the right. Got to put a little plus symbol there. I have t1 pointed to the left, and that is equal to mass b times acceleration in the x direction. In the y direction, I have a normal force up. I have the weight of mass b pointed down, and that's equal to mass b times the acceleration in the y direction. But again, it's not accelerating in the y direction at all, so that is 0. Right? How'd you guys do? So now what we're going to do is we need to merge some equations together. And the interesting thing is, really, if there's no friction, some of the forces in the y direction, most of the time, you're just doing that to get the normal force, because friction is the frictional coefficient mu sub s or mu sub k times normal force. So in this case, the y direction equations aren't going to be useful at all. It's only going to be the x direction. So what we're going to do is try to merge these two equations together. Okay? And can you see that the tension T1 is equal to mass sub a times the acceleration in the x direction, and also that mass sub a is equal to 4 times mass sub b. That's stated right here in the problem. So there's a lot of stuff going on here. So what I'm going to do is I'm going to define T1 in terms of mass b, which is 4 mass b times the acceleration in the x direction. Made a little mistake there. And so now what I have is an equation defining what the tension is in terms of mass b and its acceleration. And now you could see that this equation can be substituted into the sum of forces in the x direction on block B. When I do that, what I have is I have T2, and now that T1 is equal to 4 mass b times the acceleration in the x direction, I'm going to put that in, 4 mass b times the acceleration in the x direction, and that is equal to mass b times the acceleration in the x direction, right? Now I'm going to bring the negative 4 mass b times the acceleration in the x direction onto the other side. So I'm going to add that to both sides. And so what I'll have now, so this nils out, I'll have mass b times the acceleration in the x direction plus 4 mass b times the acceleration in the x direction. Well, add those two together, what you get is 5 mass b times the acceleration in the x direction. So T2 is going to be equal to 5 mass b times the acceleration in the x direction. So what does that mean? Well, in comparing T2 to T1, what we could see is that T2 has 5 times five times the mass b times its acceleration, and T1 is 4 times the mass b times its acceleration. That means that T2 is greater than T1. And so we've just answered this question right here, right? And if we want to go ahead and use this to get the acceleration, well, if T2 is equal to 8 newtons, as stated in the problem, well, then what we have is 8 newtons is equal to 5 mass b times the acceleration. And so 8 newtons divided by 5 mass b is going to be the description of the acceleration in the x direction. So if we knew what mass b was, if it was 2 kilograms or 3 kilograms, then we could go ahead and put that in, and we would have what the acceleration in the x direction is. So if let's go ahead and say right now that mass b is equal to 2 kilograms. Well, what that will make it is 8 newtons over 5 times 2 kilograms, and that is going to be equal to 8 over 10 meters per second squared. So we've completed the problem, but let's just think about some of this stuff. Okay, if you're pulling a rope to the right, basically the tension in this rope is pulling object B and also pulling object A. Okay, so this is, we'll call this 1 kilogram, and if this is 1 kilogram and this is 4 times that, then this will be 4 kilograms. Well, that means T2 is pulling 1 kilogram plus 4 kilograms times their acceleration. What's also can be said too is that T1 is not slack. It's tight only because it's pulling block A. If you cut that rope, well, this tension would drop to 0 and it wouldn't be pulling anything anymore. So that's the reason why tension 1 is equal to block A's inertia, mass times acceleration. Well, tension 2 is equal to block B's acceleration, is equal to block B's, block A's inertia plus block B's inertia to total 5. All right, let's move on to another problem. So these next couple slides I added because I wanted you to see other authors approaching the same problem. So this is Knight's approach to the same problem. Right here, they're just defining the problem that we just did. In this case, they're only comparing tension 2 to tension 1. They're not solving for the acceleration like we did. In this case, they're talking about what's the actual net force and other types of force interactions. And here we go. He's going to he's moving on to the force diagrams or free body diagrams. And right here we have block A. It's got a tension 1 to the right, and block A also has a tension to the left, and that is tension 2. Block B has a tension 2 to the right, and here they've defined T on A and TB on A is equal to T2. And so, as you can see, he knows the forces in the y direction isn't going to be helpful in this problem, so they're only defining the forces in the x direction. And so as you can see from right here, he's defined it in the same way, and he's found out basically that tension 1 is greater than tension 2. So they conclude also that tension 1 is pulling both blocks, mass of block B and mass of block A times the accelerations of both objects, while tension 2 is only pulling the mass of block B times the acceleration of it. So here we have another problem. We have two objects that are touching each other, so they're physically touching each other, and they're being pushed to the right, speeding up along a frictionless surface. Okay, so block A is 1 kilogram, block B is 4 kilograms, and they're being pushed to the right with a force of 10 newtons. And again, we're being asked to find the acceleration of the blocks. So go ahead and take a second and think about the number of forces acting on block A and the number of forces that are acting on block B, and go ahead and create a free body diagram for both objects. So take that time to do a free body diagram right here. So let's go ahead and start off, and again we're going to go ahead and draw a little a and a little b to distinguish between our two blocks. All right, so I'm going to draw a little A block right here and a little B for our free body diagrams. All right, and let's go ahead and think about how many forces are acting on block A. So we've got the non-contact force due to the earth pulling it down, so the weight of block A. We've got the surface of the ground pushing up on it. We've got a hand touching it, pushing it to the right, and we have block B touching it, resisting it, so kind of pushing it to the left. So let's go ahead and begin drawing our force diagram using those forces. So block A has a weight down, and I don't want to make that too big. I want to make that comparable to block B. So I'm going to go ahead and erase this and make it a little bit smaller. Block A's weight is supposed to be 1/4 of block B's weight. Block A's weight is pointed down. There's a normal force pointed straight up, perpendicular to the surface. You have a hand force pushing block A, which is contact force, to the right. And you have block B resisting block A. So we're going to put this force B on A and make it pointed to the left. So there is the force diagram or free body diagram for block A. Go ahead and try drawing the free body diagram for block B. Go ahead and pause the video now. Okay, let's go ahead and use the same method that we just did before. Let's draw the non-contact force due to gravity on block B. So its weight is pointed down. It should be larger, and I don't want to make it 4 times larger, but it's supposed to be 4 times larger. Just show it that it is distinguishably larger. All right, so it's pointed down. Block B's got its own normal force pointed straight up. And again, just like block A, the normal force should be about the same size as its weight because it's not accelerating up or down. Right? Now we have block A pushing on block B with the same force, but in the opposite direction. What I mean by that is that this force here is equal to this force here. Since they're touching and forces are equal and opposite, if block B pushes on A, then block A is pushing back on block B in the opposite direction. Right? So this is the force diagram. So go ahead and sum the forces in the x direction on block A and sum the forces in the y direction on block A. And over here, we're going to go ahead and sum the forces in the x direction on block B and sum the forces in the y direction on block B. So go ahead and do that now, and we'll go ahead and go through the solution after you attempt that. Hit pause now. All right, we're back. So let's begin, and let's go ahead and draw the sum of forces in the x direction on block A. So I have a hand force pointed to the right. I have a weight. I have block B resisting block A, and this should be pointed to the left. And that's equal to block A's mass times the acceleration in the x direction. And that's an x direction acceleration. All right. In the y direction, block A's mass is pointed, it's got a normal force pointed up and a mass times gravity pointed down. And that's equal to block A's mass times the acceleration in the y direction, but that is 0. All right, how'd you do? So we're going to go ahead and do the sum of forces on block B now. This is a little bit easier. Block B is got one less force than block A. So I just moved those two sum of forces over to give us a little bit extra room. Now I'm going to go ahead and sum the forces on block B in the x direction. So block B has block A working on it, and block A is pushing it to the right, and it has no other forces acting on it in the x direction, so we are going to go ahead and sum that as block B times acceleration in the x direction. Right, that seems done. In the y direction, I have block B's normal force pointed up, and I have block B's weight pointed down, and that's equal to the mass of block B times the acceleration in the y direction, which is 0. All right. Much like the last problem, the sum of forces in the y direction isn't going to be helpful. It's since we don't have any friction working on this, we're really only going to be working with the x direction equations, right? So we're going to merge these two equations together. And also, we have to remember that block A's mass is 1 kilogram and block B's mass is 4 kilograms. Okay. All right, and the force of the hand is 10 newtons to the right. So let's go ahead and merge these two equations together and try to solve for the acceleration in the x direction. Go ahead and pause the video and try that right now. All right, we're back. So I'm going to go ahead and mark and bring this equation on up to here. So I'm going to go ahead and write it right here. F sub h minus F sub BA, force of block B working on block A. I'll put the little vector heads on my guy there. That's equal to mass B times the acceleration in the x direction. All right? But we have to remember that force B on A is the same force. It really is. It's just the same force as the force A on B. So I'm actually just going to call both of these forces the same thing, which is equal to, we're going to call them both force AB. So I'm going to rewrite that right here. So the hand force minus force AB equals mass of A times the acceleration. That should be A in the x direction. Okay? And since we're here, this can be substituted in right there. So the hand force is now pushing block B times its acceleration to the right. And what we're going to find out when we bring over block B times the acceleration, it's also pushing block A to the right too, which kind of makes sense. It's pushing both objects to the right, and block A is actually just pushing block B to the right, but block A is being pushed to the right by the hand. So that's kind of what this is saying. So I'm going to add the inertia of block B to both sides. And that will eliminate this part and bring it over onto the other side. So what we have now is the hand force. Rewrite that a little bit better. It's the hand force, force of the hand, is pushing mass A times its acceleration, is pushing mass A to the right, and it's also pushing mass B to the right. It's pushing both objects to the right, but really it's pushing block A to the right, which is then in turn pushing block B to the right. And so now we have a way to actually find the acceleration. So the hand force, we're going to go ahead and pull out the acceleration here on the other side. So we have the hand force there on the left side, and we have block A's mass and block B's mass being combined. We're going to divide these to both sides. And that will eliminate it there. And so now we have a hand force divided by the combined masses of block A and block B, which is equal to the acceleration in the x direction. So if the hand force is 10 newtons, block A is 1 kilogram, block B is 4 kilograms, and that makes the acceleration in the x direction 10 newtons over 5 kilograms, which is going to be 2 meters per second squared. So, did we do anything that you have any questions about? Please comment in the discussion board if you have any questions on this. This next group of slides is how Knight solved the same problem. He used basically the same steps. He defined the problem right here, created a force diagram, except he created a force diagram for the hand as well. So he did a force diagram on block A, and a force diagram on block B, and you'll notice that he only looked at the x direction forces. So again, the y direction forces were not important, so he didn't use them, probably to make the problem more simple to present in the textbook. And came to this conclusion that the hand force is greater than either of the two forces, the mutual force between block B and block A, and that's only because block A was just pushing block B while the hand was pushing both the blocks. So the hand force was equal to the mass times acceleration of block A plus the mass times acceleration of block B. However, the force in between block B on A and block A on B was just because of the mass times acceleration of block B. So here we have another practice problem. You've got block A that has 4 kilograms now. It's a little bit different. And block B is now 1 kilogram. The hand force is now slowing them down with a force of 10 newtons. So they are moving to the right, but they're accelerating to the left, right? So again, you're supposed to find the acceleration of both objects. So go ahead and start off by doing a free body diagram for each object, and pause the video now. So I'm going to go ahead and start off by drawing a little A for block A and a little B for block B. And we're going to go ahead and draw a free body diagram on block A. Before we do that, let's go ahead and think about what kind of forces are acting on block A. Well, block A's got a mass, so it's going to have a weight pointed down. It's touching the surface, so it's going to have a normal force pointed up. And it's got another contact force of block B. So I'm going to go ahead and draw that right here. Block A has got a large force vector down. It's got a same size force vector up. And it's got block B working on block A, pointed to the left. Right. We're going to do another force diagram for block B, and this one, I'm going to move this over a little bit so we have some room for block B. Before we start this force diagram, we're going to go ahead and think about what forces are interacting with, what objects are interacting with block B. The Earth is pulling block B down, so it's got a weight down. Again, it's sitting on a table, so it's going to have a normal force up perpendicular to the surface. It's got a hand force touching it, pushing it to the left. Even though block B is moving to the right, it's got a force pushing it to the left to slow it down. And it's touching block A, and block A is pushing block B to the right. So let's go ahead and draw those. So I'm going to have a weight vector pointed down for block B. It's going to be negative. I'm going to have a normal force up for block B. I'm going to have a hand force working on it to slow it down. It's pointing to the left. And I'm going to have block A pushing on block B to the right. Again, these two forces are the same magnitude forces. They're just in opposite directions. So just like in the last problem, we're going to call both of these forces force A working, just force AB. Okay, just the same magnitude. I'm going to remove the vector sign from that. So they're the same magnitude. All right, we're ready to do our sum of forces. Now, in the last two problems, we've learned that without friction, you don't need to really consider the vertical forces because it's not accelerating up or down. The normal force is going to be equal to the weight of the object. And since we're not working with friction, we don't really need to worry about defining the normal force in terms of the weight of the object and thus defining friction. So in this case, let's just sum the forces up in the x direction for object A and object B. Let's do that right now. So sum the forces up for object A and B in the x direction. Go ahead and pause the video and do that now. Okay, we're back. So let's sum the forces up for object A in the x direction. Well, object A is being worked on by object B, and object B is pushing object A to the left, slowing it down. And so we have that written as FAB. And that's equal to mass of object A times its acceleration in the x direction. So it's accelerating to the left. Okay. And we have object B. We're going to do a force diagram. We're going to sum the forces in the x direction on object B. All right. Here we go. We have force AB pointed to the right, and we have the hand force pointed to the left, and that's equal to mass of object B times its acceleration in the x direction. So normally we would go ahead and, since we know the acceleration is going to be to the left, because if the objects are moving to the right and they're slowing down, that means they have to be accelerating to the left. We would put a negative here and a negative here. But let's go ahead and let the math work itself out. All right, so let's start off with right here. Well, force AB is the same thing as force BA. All right, they are the same exact force, right? So magnitudes. So I'm going to go ahead and rewrite that as negative force AB. So I make it consistent with this. And that's equal to mass times acceleration on block A. Right? And I'm going to go ahead and bring this negative onto the other side. Okay? So force AB is equal to negative mass times acceleration of block A. Now we're going to go ahead and be able to substitute that in to right here. So I'm going to take this and I'm going to bring this all the way up. I'm going to bring the sum of forces in the x direction on block B all the way up to the top right. And I'm just going to copy this exactly as it's written. This times the force of the hand. That's equal to mass B times the acceleration in the x direction. Now let's go ahead and bring force of AB, which is equal to negative mass, block A's mass times its acceleration on up, and substitute it in for force AB. So let's go ahead and do that right here. So I've got negative mass A times its acceleration minus force of the hand is equal to mass B times its acceleration, right? Now I've got to solve this, I got to do a little bit of algebra. I've got to add mass A times the acceleration onto both sides, which will eliminate from the left side. And what I'll have is on the left side now is just the hand force plus mass B times its acceleration plus mass A times its acceleration. Okay. And now I'm going to factor out the acceleration and then what I'll have, so I'll have this expression, which is equal to the acceleration plus the combined masses. What this is saying is that the hand force is pushing block A and block B, the combined masses, to the left and accelerating it to the left. And so let's go ahead and solve for the acceleration. So I'm going to divide the combined masses onto both sides. Which will eliminate it from the right side. And what we'll have is the acceleration in the x direction is equal to the hand force over the combined masses of block A and block B. So what this is saying is that the hand force, the acceleration is equal to the hand force divided by the combined masses of both objects. Now we could easily just substitute in our forces. The hand force has a magnitude of 10 newtons, so that's going to be 10 newtons. It's directed to the left. Over the combined masses, block B is going to be 1 kilogram. Block A is 4 kilograms. So the acceleration is going to be equal to negative 10 newtons over 5 kilograms, which is going to be negative 5 meters per second squared. All right. So let's review what the problem is saying. This hand is slowing down both blocks. So the force of the hand is actually slowing both blocks, and that's what we have right here. The force vector is pointed to the left. The hand vector is pointed to the left. The hand force vector is pointed to the left. And that is actually accelerating both blocks to the left, even though they're moving to the right. And so only block B is touching block A. So block A's force is being slowed by block B, while block B is actually being slowed by the hand force, which is in turn then slowing the block B is then slowing down block A. And that's how we got this. So the next problem that we're going to work on is a pulley system, which it sounds complicated. It really isn't that complicated. The only caveats to this is that you have to consider that the pulley is massless and also the strings are massless. In physics, we rarely do problems at this level where the strings and pulleys actually have a mass to them. And if we did that, it would only be when we got into rotation. So right now we're just looking at the two masses. Mass A is speeding up as it's moving upwards. Mass B is speeding up as it's moving downwards. They will both have the same velocity and same acceleration because they're attached to each other by a rope. And so we're supposed to get we're supposed to solve this problem for the acceleration, and it's going to be an equation kind of answer. So here's what the problem says: is mass A is 1/4 of mass B. Therefore, MA is equal to MB divided by 4, and we're supposed to find the acceleration of both objects in terms of those masses. All right? So go ahead and pause the video and draw a free body diagram for both objects. All right? Right, we're back. Let's go ahead and draw a free body diagram for mass A. I'm going to just go ahead and draw that right here. So mass A is right there. And let's think about what is physically touching mass A. Well, what is interacting with mass A? Well, it's got a weight down, just like it always does since it has mass. And the only object that's really touching mass A is a rope, which is pulling it upwards. So we're going to go ahead and draw that over here. So mass A has a weight down, and I'm going to draw a smaller arrow so that I can be consistent with mass B. And it's got a rope up with the tension, we're going to call that rope T, pointed upwards. There is no normal force on this object, on either object, because they are not touching the ground. They're just in the air. Right? And mass A is accelerating upwards. I'm going to draw that here to refer to that arrow. Now let's go ahead and do mass B. Mass B, let's do a force diagram for mass B, and I want you to draw that right now. So pause the video, please. All right, we're back. So mass B has a long vector down, and it's the weight of mass B times gravity, and it's got one contact force. Again, it's the same rope that is touching mass A. Let me fix that vector here. Sorry about that. And I'm not sure about the sizes of these arrows. I'm just drawing arrows. I don't think they're going to be the same size up and down, but I'm not sure. Okay, so I'm just noting the vectors. And they're probably not the same size. So I'm going to draw this one to be a little bit smaller. Since it's accelerating down, the net force is going to be down on object B. So that means the upward arrow is going to be small. The upward arrow is going to be smaller than the downward arrow. And on mass A, since the net force is upwards, since it's accelerating upwards, the downward arrow is going to be smaller than the upward arrow. This is accelerating, so mass B is accelerating down, therefore the net force is going to be down, and that means the down arrow is going to be larger than the up arrow. Mass A is accelerating upwards, and that means the up arrow is going to be greater than the downward arrow. So the acceleration vector tells you the direction of the net force. So that means the sum of the forces up has to be greater than the sum of forces down if the acceleration vector is pointed up. Right? Let's go ahead and sum those let's apply Newton's second law for mass A in the y direction, and apply Newton's second law for mass B in the y direction. Go ahead and pause the video and please do that. All right, we're back. So this is going to have a positive acceleration. This is going to have a negative acceleration. Make sure to draw those. They're going to be very important. Since we're only using equations, they're going to become important right here. Okay? So T, so we're doing object A. It's going to have a tension upwards. The rope is pulling it up. We have its weight vector pointed down, and that's equal to an upward pointed mass times acceleration in the y direction. For object B, it's also got the same rope attached to it, and that is and its weight pointed down, and it is accelerating down. So that's why it has a negative. Mass A was accelerating up, that's why it has a positive. So what we're going to do is we're going to go ahead and combine these two equations together. Now, it doesn't really say this in the problem, but I think they want the answer in terms of mass B and gravity. So we're going to go ahead and we're going to evaluate, we're going to substitute in for everywhere we see a mass A, we're going to put in mass B divided by 4. So again, mass A is equal to mass B divided by 4. Okay, so we're going to plug that into here and here. So we have a tension vector pointed up. We have mass B divided by 4 times G, and that's equal to mass B divided by 4 times the acceleration in the y direction pointed up. Okay? So what I'm going to do, I'm going to go ahead and take this equation and solve it for t. It doesn't matter which one you do in this case. We need to combine these two equations together. And the only way to do that, they have a common variable t. So I'm going to take the simpler one, this one, solve it for t, and then we're going to substitute into this t, and then reduce down as much as we can and try to get an equation to talk about what AY is equal to. Okay? So I'm going to add MBG to both sides. Right? And when I do that, it gets rid of it from the left side. So now I'm going to have a tension minus MBAY plus MBG. And now I'm going to plug this into here. Okay, so I'm going to bring this down here. So now tension, which is MBAY plus MBG, that is the tension in this equation right here. And now I'm going to carry on with the rest of the equation. So that is negative MB over 4G plus MB, whoops, forgot an equal sign. So equals MB over 4 AY. So again, this is T right here. This is the tension T from this equation. And the rest of this part is the rest of some of the forces in the y direction on block A. Okay. So now I'm going to put my A's to the left, and I'm going to bring my G's onto the other side. Well, actually, hold it. I'm just going to bring I'm going to bring this onto the other side here. It'll be easier. So I'm going to add MBAY. Again, the whole point is to get an equation to evaluate the acceleration in the y direction. So I'm going to add this to both sides. And it's going to eliminate it from that part. So now I'm going to have MBG minus MB over 4G equals MB over 4 AY plus MB AY. Here I'm going to pull an MBG out. And I get 1 minus 1/4. Over here, I'm going to pull an MBAY out. And I get 1/4. Whoops. Plus 1. So this becomes MBG times 3/4 Or I could actually say that this right here becomes 3/4 and this becomes 5/4. And so 3/4 times MBG equals MBAY times 5/4. I'm going to fix that 5 a little bit so it's not so strange looking. Notice that the MBs cancel out and the fourths will cancel out. I'll let that happen naturally. I'm going to multiply both sides. So I have, what I'll have is 3/4 G. I just brought 3/4 to the front. The MBs came out. And that's equal to 5/4 times AY. Right? The 4s will cancel out. And what we'll be left with is 3/5 G, and that's equal to the acceleration in the y direction. Okay. So if the blocks are, so if block A is speeding up as it's moving upwards, and block A is less than block B, and block B is pulling, is falling downwards, and then thus the rope is pulling block A upwards. What you find out is it's not falling at gravity. It's actually somewhat less than gravity, 3/5 of that. All right. All right, let's move on to the other problem. So here we have the last problem before we start on the lecture tutorials. This is a practice problem, and again, it's another pulley problem, and this is what is called a modified Atwood machine. Right? In this one, block A sits upon a frictionless surface, and it's got twice the mass of block B. And I'm actually going to give some context to this. I'm going to say, just really quickly, that block B is 1 kilogram, and block A would then be 2 kilograms. So that means block A is 2 kilograms, and block B is 1 kilogram. Now I want to do that for a very specific reason, which we'll talk about in a second. So if it's frictionless, and the problem is indicated that block A is going to be speeding up as it's moving to the right, and then block B is going to be speeding up as it's falling downwards. And so the reason why block A is moving to the right is it's connected to a rope on to block B, and it also sits upon a frictionless surface. So it's really easily it's going to really easily be able to slide. So here we go. We're going to have block A, which has got, so I'm going to again draw block A and block B to distinguish between the two. All right. So what I want you to do is pause the video, and I want you to go ahead and give me a free body diagram for block A in this case, and give me a free body diagram for block B in this case. And we're going to work our way up to the acceleration of both objects. Okay? Pause the video now. All right. Let's keep moving. Let's do a free body diagram on block A. So block A is it's got a weight downwards. It's sitting upon a surface, so it's going to have a normal force pointed up, perpendicular to the surface, and it's got a rope attached to it, and ropes pull, so the rope is going to be pulling it to the right. All right. So block A has a weight downwards, which is mass of block A times g. It's got a normal force pointed upward. And that normal force, since the object is not accelerating since block A is not accelerating up or down, that normal force should be the same size as the weight of the object. And since there's only one normal force acting here, since block B is just hovering off the ground, it's not touching the ground or the wall, I'm just going to call that N. All right, block A is being pulled to the right by the rope. So I'm going to call that rope T for tension T. All right. Now I want you to do a free body diagram on block B. Pause the video and do that now. Okay, we're back. So block B is 1/4 the mass of block A, so therefore its weight vector is going to be smaller. And block B only has one contact force, which is the tension T. And so even though the rope is in this case pointed is pulling it up, so the object is falling down, but the rope is still pulling it up. A lot of people wouldn't think that the rope would still be pulling on this object, but it still is. Ropes only pull, okay? And it's not slack or anything like that. It's a taut rope. And so what I'm going to do is I'm going to draw this vector up, and this is the same rope that is over here working on block A. So that means, since it's the same rope, it's going to be the same force. So this vector should be the same size as this vector. Okay, let me try to make that look the same here. Okay. So they're about the same size. Okay. So what I want to do is I want to sum the forces in the X and Y direction on block A, although it's not necessary to sum the forces in the Y direction since there is no friction force. Again, the normal force, evaluating that in the Y direction is going to be very important. And block B is going to be accelerating down. So this sum of forces in the Y direction upwards is going to actually be smaller than what I've indicated. Okay, so the tension force has to be less than the weight force because it's accelerating down. Okay, it's accelerating down in the Y direction. The sum of forces has to be greater down than up, which is going to make this rope force even smaller than what I've indicated here. And try to make sure this T is the same size as this T. There we go. So block A is accelerating to the right and block B is accelerating down, and since they're connected by a rope, they have the same acceleration vectors. So right now, let's only sum the forces in the X direction for block A. The reason why we only need to sum the forces in the X direction on block A is that since there is no friction, normal force is not going to be important. Not only that, it's not accelerating up or down anyways. Only block B is accelerating up or down. So we're only going to try to evaluate now the sum of forces that are relevant to the actual problem that we're working on. So go ahead and sum the forces in the X direction on block A, and I want you to go ahead and sum the forces in the Y direction on block B, because there is no X direction forces acting on block B. Go ahead and do that now and pause the video. All right, so in the so for block A, what we have is we have a tension force pointed to the right, and that's equal to block A times the acceleration in the times the acceleration in the x direction. But that acceleration is this acceleration. So even though this is in the y direction, this is accelerating in the x direction. Again, they're attached by a rope, so they'll have different directions but the same magnitude. So I'm just going to call that acceleration, not acceleration sub x. In the y direction, on block B, we're going to go ahead and sum those forces right now. So it's got a tension up, and that's the same tension as up here. It's got a weight vector down, and that is equal to negative mass B times acceleration. Okay? So remember also that mass A is equal to 1 kilogram, and that mass B is equal to 2 kilograms. Okay, so when looking at this problem right now, if this is 1 kilogram and this is 9.8, I'm thinking that this acceleration should actually be falling at gravity. All right, so that could be an assumption that I could make. I'm not sure if I'm right, but it was something that I would guess to be true. So let's go ahead and find out if that is true. Do you agree with me, or what do you think? Do you think this is accelerating down at gravity, since this is equal to 1 kilogram, and all objects should fall at the same rate? And this is frictionless, shouldn't this be accelerating to the right and this be falling at gravity? So that means this acceleration actually should be gravity 9.8 meters per second squared to the right. What do you think? Well, let's find out if that's true. So I've got an evaluation for tension right here, and I'm going to go ahead and substitute that in to our Newton's second law for the B object in the y direction. And what I get is mass of block A times the acceleration, and that is our tension. Well, block B is got a weight down, and here block B has the acceleration vector down. Okay. Now I'm going to bring this to the right hand side. It's plus over here, so this is going to be, I'm going to bring it on to the right hand part of the equation, so I have to subtract it from both sides. When I do that, it eliminates it from the left hand side, and I got negative mb times g, mass of block, the weight of block B, and that's equal to the acceleration of block B minus block B's block A mass, the mass of block A times its acceleration. So I have negatives everywhere. You can multiply through by a negative, and what you get is, you just get this. You just get positives everywhere. Okay. And so this is going to be mass of block B times the acceleration plus mass of block A times its acceleration. Now I'm going to factor out the acceleration, and now I get the masses of block A and block B. This is a mass of block B times G. And let's go ahead and divide both sides by MB plus MA. And what I get is, I get acceleration is equal to mass B over G over mass B plus mass A. Well, mass B, we're saying, is 1 kilogram, So that's 1 kilogram times g, which is 9.8 meters per second squared, divided by 1 kilogram plus 2 kilograms. What that means is that acceleration is equal to 9.8 newtons. 1 kilogram times 9.8 meters per second squared is 9.8 newtons over 3 kilograms. Which is basically what we're saying is that's 1/3. And pull up my little calculator. So that is 1/3 of gravity. So that is going to be equal to 9.8 I don't know how I got into programmer mode. I apologize. 9.8 divided by 3, which is 3.27. So this works out to be 1/3 of gravity. By guessing that this was falling at gravity, we forgot the fact that this has inertia, and it's actually going to slow it down, and it's not going to be falling at the acceleration due to gravity because of this extra inertia off to the side. So even though this is frictionless, it has inertia, and that's actually going to keep this object from falling at gravity. Interesting. So I've just done a bunch of problems that are related to our homeworks, but also to the worksheets, to the lab tutorials by Dr. Summers. So the general things that you should have learned here is basically the problem-solving principles that you should have learned was to, first of all, when you look at the objects, you're going to have multiple objects now, so you're going to be doing multiple free body diagrams, and you have to try to get as simple as you can. Okay, so for each object, you're going to only look at what is physically touching the object and also the weight of the object, which is non-contact force. And then you're going to try to draw those and sketch those as accurately as you can. And then you're going to look for areas into which to combine those equations together. So once you sum up those, once you do the vector addition and apply Newton's second law and sum the forces in the x and y direction for each object, you're going to try to look for common variables that they have. So again, look for what is interacting with each object. Okay, and what Knight does is he draws an interaction diagram, and he uses this in forces but also in energy. Okay, and then try to think about what is affecting the accelerations. So in some cases you're going to have accelerations. You will actually have the same magnitude acceleration, but some objects may be traveling in the x directions and the other objects may be traveling in the y directions. So really, this is where you really have to think about what is going on. And some objects will be traveling, accelerating up, and some objects will be accelerating down. And they may have reverse, the velocity vectors may be reversed to that. So really, you have to really think about the accelerations here, acceleration vectors. All right. So go ahead and move on to the lecture tutorials. All right. The first lecture tutorial is a lot like what we've just done. And a couple tips here. Again, you're going to draw a force diagram for object A, or a free body diagram for object A, and you're going to do a free body diagram for object B. First, start off by drawing the non-contact forces, and then start asking yourself what is physically touching each object. And so this first one is object A, which is the one up here that's pinned against the roof. So ask yourself, what is physically touching it? And also make sure you also include the weight of the object too. Object B also has weight, and also what is physically touching it. So so this may help you out. Object A has a weight vector, okay? It's touching object B, and it's also touching the ceiling. Object B has a weight vector, but a hand is touching it, pushing up on it, and object A is pushing down on it. So object A has object B touching it, and object B has object A touching it, and they're in opposite directions. Okay, so please work through all of these lab tutorials. And what you're going to have to do is you're going to have to open up a drawing object and probably draw the vectors, and then you could label them with a pen. Right? And if you need to know how to do that, there's instructions in the lab tutorials on how to draw those. Okay? Good luck.